So in this video, we're going to learn how to write cell notation. And cell notation is a way to avoid drawing these pictures of electrochemical cells. So at the end of the last video, we set up this electrochemical cell. We used a zinc anode and a copper cathode. We immersed it in a solution containing zinc ions and copper ions. We used a salt bridge to keep the solutions electrically neutral, and we measured the voltage, and the voltage is somewhere on the order of 1.1 volts. And it would really stink if we had to keep drawing these pictures of cells and electrodes and salt bridges, and so cell notation gives us an easy way to represent this. Cell notation, we normally start with the anode on the left and the cathode on the right, and if you just remember, that's alphabetically ordered, so A before C. That probably helps you remember. So my anode is the zinc. Okay, it's all the way on the left. Okay, in fact, the tradition is to write the electrodes all the way on the left and all the way on the right. So I'm going to write the copper, which is the other electrode, all the way on the right hand side. And the electrode is really just the thing that we connect the wire to. We can't connect a wire just to the solution by itself. So this is my cathode. All right, so that saves us a little bit of time. All right, what we're going to do now is we're going to write a line every time there is a phase boundary. And what I mean by that is that this is solid zinc and this is aqueous zinc ions. And because it's a different phase, so this is a liquid phase and this is a solid phase, we are going to use a vertical line to represent that phase boundary. If you like, you can imagine, if this is a microscopic view, that line represents the barrier between being a solid and being in the liquid phase. Okay, there's a little more to it than that, but you'll have to learn about that in another course. So then I've got my zinc ions, so I'm going to go in and indicate them like that. Although I can't just have zinc ions by itself, I would need something like zinc nitrate. The nitrate is not responsible for anything here, so I'm just going to ignore it. I'm going to write its aqueous, and I'm going to write its concentration. It's 1 mole per liter. Okay, I didn't give myself enough room here, so let me go ahead and try and move the right-hand side over a little bit. All right, that looks a little bit better. Okay, so on the other side then I've got my copper dipped into a solution of copper ion. So there's a phase boundary. There's the liquid phase, there's the solid phase, so hence my vertical line. And the copper is copper 2 positive, and it is aqueous, and it has a concentration of 1 mole per liter. In fact, you might recognize that's our standard state concentration. So we're going to indicate that this has a standard state voltage here by using our normal symbol, the degree symbol. All right, now the salt bridge is interesting because you can think about there being a phase boundary at each end of the salt bridge. There is essentially a solid here that it represents a phase boundary here and here. And you might say, well, how do you know there's a solid? If it wasn't there, the solutions would just glug, glug, glug and mix through. So the convention then is for the salt bridge to do 2 lines, each line representing one end of the salt bridge. Now, later on, you'll see that every time there's a phase boundary, there's a small voltage created due to the phase boundary. And in this course, we're going to completely ignore that. But later on, you'll see that those lines have another meaning. So, okay, so maybe I'll write some things down here. I said it verbally, but the very far left and the very far right is where we put the electrodes. So the electrodes go on the ends. The double vertical line represents our salt bridge. And you can see this is way, way, way easier to write this out than to write this out. So now you know how to understand cell notation.